I'm working on that. We'll be live in a second.
I think we are live. Let me just double check it.
Hello, Vlad.
We are live. Okay, so once we are live, I would like to welcome everybody back to this renewed time for the Quantum Matter seminars. Adrian and I hope that you all had a great time during this vacation that we had over the past month. And we are very excited because just think that currently we are closer to normal days than we were the last time we had in this venue with the vaccine. So we are really excited. Of course, the pandemic allowed us to receive people from all over the world. And for us, it's a very real pleasure to have a friend, our Brazilian friend, Eric Andrade, from the University of São Paulo, talking about the perturbing the Kitaev model. So Eric, thank you very much for accepting our invitation. The stage is all yours.
Thanks, Chris, and thanks, Adrian, for the really nice invitation. And as I was talking to you guys, it's really a pleasure to be in this series. I mean, I've been following this from afar. I mean, we have a really nice program. I mean, it's really a pleasure. And thank you all in the audience for coming. And I hope you enjoy the work. So I'm gonna discuss the Kitaev model. I mean, this is really nice model. I'll talk about a little bit about it. So and then the idea is we'll perturb it two different ways. So I'll explain what I mean by perturbing it. So this first, let me acknowledge the people which actually did the work. So the first part of the work I'm going to show is really a work from our former master student, Pedro Consoli. So this is a follow-up work which I did in collaboration with Lucas Jansen, Matthias Voigt in Dresden, and now Pedro moved to Dresden to do his PhD in Matthias' group. So I mean, so this is the work we're going to discuss, follow up from these two earlier works. And now in the second part of my talk, I'll discuss recent work I've been developing with my master student, Vitor Meirelles, here in São Carlos. So hopefully this should be soon in the archive, and I'll show you the results you have. And also I'd like to acknowledge the Brazilian agency and PQ and FAPES, which gives us the money to actually carry out this work. So, I mean, this Kitaev model, it falls within this range of frustrated magnetism. So just to give you a really brief overview. So whenever we talk about frustrated magnetism, we always think about this triangle or odd loop lattices in which you have antiferromagnetic couplings, and then therefore it's not possible to satisfy all couplings at once. So in the particular case of triangle lattice, we know the ground state, which is actually ordered this non-collinear state, but the frustration, I mean, this is what comes to mind. So it's really about local spins, and you have antiferromagnetic couplings, and then somehow the geometry or something else forbids you to satisfy all couplings at once, which means we would like to have the most collinear arrangement of spins, and frustration does not allow it. So we are really talking about, so if you just draw some sketch here, so this would be the Hubbard-like U, so this would be the localization of the electrons, really talking about localized electrons, so large U, and then this parameter will turn up frustration. So as we increase the frustration, then usually you would order like an antiferromagnet order, so frustration is small, but then if you start to increase frustration, then you can go to somewhat like spin liquid phase or something else where you do not have long range order. And it's also interesting in particular, so if you are close to the mod transition, you can also have a spin liquid before going to an antiferromagnet to an ordered state. So for instance, this is an example discussing the triangle lattice. I'll not be talking about it because this is nice physics, but I'm really interested in the strongly localized regime and strongly frustrated regime. So this is the regime which I'm going to talk about. So it's really about localized spins in a frustrated lattice or with frustrated interactions, which I'm going to show in a second. So experimentally, it's kind of easy in principle to identify possible candidates for spin liquid. So for instance, the first thing you can look up is the, let's say, the thermodynamics. So you can look up to the susceptibility here. I just showed the sketch of the inverse susceptibility as the function of temperature. Then you can calculate the key revised temperature, and then you can look up the actual temperature where the system order, which I'll call T star. So I mean, if you have a large difference between T star and the key revised temperature, so it means your system is frustrated somehow, and you really need to go to lower and lower temperatures to order. So in principle, you would like to push this T star to 0, so do not have order. But even though, I mean, even if the system orders really low temperature, you are now frustration. Generally, what it does, it pushes the energy scales to lower and lower temperatures, and now new phenomena emerge, like order by disorder and several other interesting aspects. So this is really more or less how we can have a glance experimentally to look to frustrated systems. I'll discuss a bit more of experimental results by the end of the talk. So, but now inside these frustrated systems, I'm gonna talking about this Kitaev model. So this was originally proposed by Kitaev in 2006, and there is a nice follow-up work next year by Bhaskaran and Alvin Shankas, where they discuss several nice properties of this model. I guess Kitaev's original idea was to apply this to topological quantum computation, and Bhaskaran and these co-authors, they brought this more to condensed matter side. But anyway, so this is the model. So it's really a model which is the interactions. S is just the spin on each side, K is the Kitaev coupling, nearest neighbor only, and it's kind of Ising-like in the sense that only one component of the spins interact, but it's kind of it's funny because it's a funky interaction, because let's say along this blue bond, which I'll call Z bond, on the Z component of the spin interact, along this Y bond, along this green bond, which I'll call Y, just the Y component of the spin interact, and the same is the same along this red one, which I call X bond. So in principle, the frustration comes from the fact that you cannot, that the spin cannot choose. I mean, it cannot be parallel, let's say, cannot order along Z, nor Y, nor X, because if you order along one, you frustrate two order. So in this case, I'll be discussing mostly the honeycomb lattice, which is not frustrated, but in principle, this model you can apply it to other track coordinate lattice like the hyper honeycomb and many others. But my main focus will be really on the honeycomb lattice, which was the original lattice for which the model was proposed. So what's funny, because this is not a frustrated lattice, but the interactions, let's say the K term makes it's frustrates the model. So I'll call this orbital frustration or exchange frustration. It will be clear in a minute why I'm calling this orbital frustration. So, I mean, how can we see this model is frustrated? So we can play like the usual game in the field. You can go to the classical limit, let's say, you just put this, you say spins goes to infinity, or you treat the spins like vectors. And then all you have to do to find, let's say, the magnetic ground states, to take the Fourier transform of your couplings, like I sketch here, J of Q, where Q is momentum. So you go to momentum space, take the Fourier transformer for J, and then you look for the minima. So if this guy has a minima, generally this minima will correspond to the Q vector, the order wave vector, and then you can more or less identify your long range order. So that would be the starting point. In this particular example of the Kitaev model, actually, if you go to the moment space, you find a flat band. So there is no minimum. So in principle, all points in the Brillouin zone are potentially Q vectors. So then you really have a classical system with massive degeneracy. So this is a hint. You may have something interesting in the S equals 1/2 case or lower spin. Actually, you can have it's one way it's a promising way to look for a quantum spin liquid. But luckily for us, so this is not a speculation, but Kitaev showed us that this is actually the case. So he was able to solve this model. So, and then he really showed we have a spin liquid in 2 dimensions in this model. So, I mean, how this solution works, or so most of you probably know it already, I'll just sketch this for you, because I'll come back to this by the end of the talk to discuss a bit of results. So Kitaev's original idea is you write your spin, let's say at site J, as the product of 2 Majorana fermions. So you call one Majorana fermion 0, and the other Majorana fermion gamma, C gamma, where gamma is X, Y, and Z. So corresponding to the 3 different bonds in your system. So you introduce this. So you introduce this 4 Majorana fermions. So they are Majorana, they are emission fermions, they obey the anti-commutation rules. So, and then what happens? Well, basically what happens when you use this representation, something really interesting happens. So it's like it's sketched here. So you basically break up your spin into 4 Majoranas, and then you can think like 3 of these Majoranas, let's say the green one, the blue ones, and the red ones, they kind of live on these bonds, so they are localized here, and you just have 1 Majorana left, which would be the 0 Majorana, or this yellow Majorana, which can freely hop around the lattice. So basically, you are able to map your spin system into a system of 3 Majoranas hopping in lattice. But that's not the full story. You still need to fix, to restrict your Hilbert space, because a maneuver represents your spin by a Majorana fermions. You have to apply a constraint. But what Kitaev was able to show was the following. It's an interesting thing. Actually, you have you can define, let's say, the flux around the plaquette, which would be, let's say, the product of the 6 spins around this plaquette, like shown here, with the proper component of the spins, like I sketch here. But actually, you can write this in terms of this U variable, which with just the links around a single hexagon. And this U is just, like I said, just this product of the 2 Majoranas living in a bond. And this guy, this W, actually the U's are conserved quantities. So all you have to do to solve this model is really to fix these U's, like, let's say, the ground state, actually you can put all U's with the same sign, which means no flux, and then you just have Majorana fermions hopping around. So this will produce to you a graphene-like dispersion for Majoranas, which is sketched here. This is borrowed from Kitaev's original work. So basically, then you have 2 kinds of excitations. You have what we call Wison excitation, which would be to create a flux or to flip a bond. And then you have the Majorana excitation. The Wisons, they are gapped. So basically, we assume you're in the ground state of the Wise, and the low energy excitations are given by the Majorana, which have a graphene-like dispersion. With the difference, you just have 1 branch. And then what is also interesting, which Kitaev shows, that if you apply an external field, in particular in this one, in a particular direction, he was able to show. So you open a gap in this graphene-like dispersion, and this is actually a topological gap. So in principle, if you calculate the, let's say, the thermal Hall response, you are able, actually, in your thermal current, you are actually able to find a quantized chiral Majorana edge mode. So that in principle would appear in this topological phase for this model. So this is nice. This was a really nice proposal. So, and actually there are experiments in this Kitaev-like material, which is alpha routine trichloride. So actually, this is a material which is a Kitaev material. It's a candidate to show this Kitaev-like interactions, and this has a really nice phase diagram, which I sketch here. So this is temperature, this is external magnetic field. So if you do not have magnetic field, actually this material, it does show long range magnet order, this kind of zigzag order. So I sketch here. So you just have spins in this kind of zigzag pattern. I'll discuss this in more detail. So this means you probably do have some Kitaev interactions, but you have some other interactions which makes the system actually orders. But what's interesting, what people figure out, like really early on, so if you apply a field, you kind of melt this order, and then there is an intermediate region before you go to the, let's say, to the polarized regime of the trivial paramagnetic regime at really high fields, and then there is this intermediate region where in principle you find some topological signature, exactly like Kitaev proposed. So there is in principle this Nature from 2018. There's a recent science from this year. So people were actually able to measure the thermal conductivity, so the transverse thermal, or the Hall response. So, and they were able to show for different field directions. So this is the field, and then as you increase the field and you reach this topological region, this guy reaches a plateau where the value half here means you really have a Majorana. And then people are actually able to show, if we invert the sign of the field, you actually change the sign of the response as you expect for the Kitaev model. This is just a blow up. So this is really a good let's say, a promise signature that's kind of Kitaev physics may be realized in real materials. And then there's a lot of interesting theoretical discussion. I mean, how response can happen, how it couples with phonons. I mean, this is really interesting. And I just point out there's also recent work which shows some kind of quantum oscillations in this thermal response, which does not actually fit this Kitaev scenario and show there is much more going on, but at least I would say this is a promise venue to realize the Kitaev physics. So, and how does this Kitaev physics comes about? I mean, can we understand, like microscopically, how you can generate this kind of funky interaction? I mean, this is not what one would expect more by our regular magnet. So actually, if you now you need to think about, let's say we talk about 4D5 or 5D5 materials, a particular ruthenium and iridium. So you have to have these heavy materials because you need spin orbit coupling, strong spin orbit coupling is the key ingredient. So you imagine you have your d orbitals with 5 electrons, and you place them on an octahedral crystal field. So this could be either a chlorine or oxygen, depending on the material. The blue guy would be the magnetic ion. So then you generate the T2G in the EG orbitals. And then now, because of the strong spin orbit coupling, you split the T2G orbitals into 2 orbitals, which have an effective J moment 3/2 and a effective moment J equals 1/2. So this is just like a single band materials with just at half filling. And then you have also U, a Hubbard U, which brings this into the Mott insulating regime, and then we can talk about localized moment physics. A key ingredient for the Kitaev physics to emerge is that this octahedra, they actually have to share an edge, like I show here. So because in this particular configuration, you are able to suppress the, let's say, the J term or the Heisenberg term, and the Kitaev term gets enhanced. So, I mean, if you have all these ingredients, in principle, we have hope to find this Kitaev-like interaction. This will actually show early on by Jacqueline and Kaliuli, and afterwards by Chalupka, Jacqueline and Kaliuli in a series of nice work. And there is this nice extension also. You can have more terms here, like a gamma term, gamma prime term, and so on and so forth. But at least now we have a microscopic understanding in which kind of materials we can find the Kitaev term, but also becomes clear that it will be hard to find just a Kitaev term. So you have perturbations, in particular, the one relevant perturbation would be the J term or Heisenberg term. So also I'll consider an external magnetic field. So this somehow motivated people to study the, let's say, the so-called Heisenberg Kitaev model, which basically you keep the Kitaev term, so you can parameterize like the K term, which is Kitaev by an angle phi, and then you can add like a J term, which is the Heisenberg term, and then you can basically tune between the two by varying this angle phi. So actually, if you have like phi equals 0 and in the L phase, phi equals pi, you are in the ferromagnetic phase, and if you have phi equals pi over 2 or 3 pi over 2, you are on this actually on the Kitaev spin liquid phase, and you can really see this liquid phase, it's stable up to a certain region, so it's nice. So you have a finite region to find the liquid phase, but also find other ordered phase. Particular ordered phase you find is the zigzag phase, which people see in experiments. So this is good because it means somehow you can think about it can be close to the liquid phase. So in principle, there is hope. If you perturb it, you can go to the liquid phase. So in one way to perturb this model is really to apply, let's say, an external magnetic field. So, and now that will be the focus of the first part of my talk. So then now I'll kind of leave aside the liquid phase, which is kind of maybe what somehow that's the most interesting thing on the model, but I'll leave it aside and I'll discuss these ordered phases because, I mean, in principle, the materials, they have this ordered phase, and then we'd like to understand them and see more or less how close are we to the liquid phase. So in one way to perturb this model is really to apply an external field. And then something interesting happened if you just think for 30 seconds, because the Kitaev term, the model now becomes anisotropic in spin space. So usually, if you have an isotropic model, like with SU2 symmetry or something like this. If you have, let's say, an antiferromagnet ordering, if you apply a field, you just have a uniform canting until you go to the critical field. So spins just cant towards the field, and that's it. But if your K term is different from 0, so in principle, your system can point in certain directions which do not allow you to have an uniform canting. So now when you have a field, you can have some sort of non-uniform canting, which means you have different angles for each spin in the magnetic sublattice. And this brings about an interesting physics, because now, because of this, you have now more subtle energy competition, and then you can find different phases in your system when you apply a field. So this is an interesting thing, which we explore this in our earlier work. So now let's just look to the phase diagram, the classical limit. So S going to infinity. So basically in this limit, the Kitaev spin liquid shrinks to 2 points. So I show here. So this point here and this point here, those are the, let's say, that would correspond to the liquid phase, in which in the classical limit is just a point with no long-range magnetic order and extensive degeneracy, as I discussed before. So this is the phase diagram for a particular field direction, which I call 0, 0, 1. So I'm thinking about this refers to cubic axis in spin space. So this is the language. So I'm really talking about the cubic axis in spin space. So what happens is all this phase, the zigzag phase, the stripe phase, and the nail phase, they have the property that order by disorder makes that the spins, they all point along one of the cubic axes. So let's say the spins either point along X, Y, or Z. So that's what order by this, that's what fluctuation does to you. And therefore, if you apply a field along this direct 0, 0, 1, it's possible for all these phases to cant. So they just cant towards the field, and then you reach the critical field and you go into the polarized phase. So this is more or less the usual scenario. So for this particular field direction, what's kind of interesting, so those are the all phase. So just to stress, this is just the stripe phase, nail phase, and zigzag phase. They are written here. I'll keep this color code, but I'll keep coming back to all these different phases. But the main message is, for this particular field direction, you can just cant towards the polarized phase. But now, if you apply a field like in this diagonal direction, 1, 1, 1, something different happens, because now you cannot have a uniform canting towards the polarized phase. And then you see, so what we advertise actually happens. So first, let's focus on the zigzag phase here, the canted zigzag. So now it's kind of hard to see. So, but the size of the arrows here are different. So you get a non-uniform canting, and the transition towards the polarized phase is actually first order. So it's no longer a second order phase transition as you had on 0, 0, 1. And also something different happens here. Instead of have zigzag phase, you have the so-called AF star phase, which is shown here. It's kind of complicated phase with 8 sides per unit cell, and always you have two spins, 1 points towards the fuse and another 1 point opposite to the applied fuse. So it's kind of more complicated phase. And it's interesting because as you increase the field, you go to a vortex phase, and then this vortex phase melts to a polarized phase. So, and a similar physics happen on the ferromagnetic side, so to say. So you just change the zigzag by stripe, antiferro vortex by vortex, AFM star by FM star. So that's essentially the reason what this non-trivial energetic competition gives rise to new phases. So this is basically what we did in 2016, 2017. And this was a nice work because it already showed something interesting, which people explored so much afterwards, that the antiferromagnetic Kitaev point has a much larger critical field than the ferromagnetic critical point. Of course, I mean, if you do for spin 1/2, we now know that you have an intermediate spin liquid phase, but even at the classical level, you already see that there is asymmetry. Although the solution for the pure Kitaev model does not depend on the sign of the coupling, in the presence of the field, the sign of the coupling is already changed the physics considerably, as people have been exploring a lot in the last years. But I won't go to this. I'll mainly focus on this part on the ordered phase. So let's see what can we learn.
So Rick, I have just a short question before you go on.
Sure.
So this is the ground state, I assume, right?
Yes.
And now these are broken symmetry. Some of them are broken symmetry states. When you raise the temperature, are these all transitions second order, or there are some which are first order most?
That's a good question, Vlad. I didn't explore this in detail, although I did the Monte Carlo simulations. That's a good question. So the honest answer is I didn't check them all. So I'm sorry. But let's say I check for, let's say, for the vortex, this is second order, but I didn't check for all of them, Vlad. So in principle, they could be first, second order. I didn't check in my simulation. I did the Monte Carlo, but I didn't check these details.
In many striped, in frustrated magnet, stripy phase are common, and many times when you have competing interactions, even in old style classical statistical mechanics models, when the frustration is strong enough, it makes kind of the transition usually first order, even when you think it should be. I mean, there is nothing fundamentally preventing it to be first order, so that's not uncommon.
That's true. Thanks for the question. So I actually didn't check, so that was my fault. But in principle, I did the Monte Carlo simulation to find the ground state, but I didn't check this in details. But you have a point. Thanks for pointing it out. So, and then, that's what we did. And the next thing, then we decided, okay, so let's, together with Pedro, so they decided, let's try to do some spin wave correction. I mean, this may be interesting to see. I mean, how stable are those phases? I mean, we can try to play around and we can do spin wave on top of this ordered phase. So that's why I'm focused on ordered phase. So basically just expand our Hamiltonian powers of square root of S, so the usual game. And then when you start to play with spin waves, you quickly realize something interesting in this model. So here I just show two equivalent in principle definition of the magnetization along the field direction, or the uniform magnetization. So you can either calculate this by the derivative of the ground state energy, or you can calculate this as just summing up the moments along the field direction. So that would be the angle theta, which is the angle which the spin makes with the external field. So, okay, so let's focus on the first definition first. So we can calculate, let's say, this is the classical ground state energy, this is the quantum corrections coming from spin waves. And then you can just derive it, and then you can just take the derivative, and then you can plot the magnetization as a function of the field. So this is just for the Néel, for the Heisenberg point, where not have the Kitaev term, and then it has the expected behavior. So the quantum fluctuations reduce the magnetization, and then the quantum fluctuations go to zero at the transition because the polarized state is a ground state of the Heisenberg Hamiltonian. Then you have it. So the critical field does not change. But then quickly, as you turn on the Kitaev term, something really interesting happens, even for the 0, 1, 1 direction, which is the simple one. So you see, in principle, the magnetization can even go above the classical curve. So this in principle is fine, nothing prevents it. But which is not what's not fine is the fact that you get a saturated magnetization before for a finite field, and that cannot be because the polarized state is not the ground state of a Hamiltonian. Then you realize the linear spin wave is not enough to discuss your results. So this is the first hint we had. Because I mean, in principle, you can only have the fully polarized state at infinite field, because the Kitaev term, the polarized state is no longer an eigenstate of the Kitaev Hamiltonian. So the linear spin wave is consistent. And how did we interpret this? So our interpretation is the following. Actually, you have a reduction of your critical field. So this correction of this angle is actually negative, which means you arrive earlier at the critical field. So that's essentially our interpretation of this. And then I'll show you how we elaborate a nonlinear spin wave theory, which is consistent. So that's essentially, that's the problem which we identify, and that's what we did. So basically, we follow this earlier work by Zitominsky and Ikuni. So we did something really simple. So we just did mean field decoupling of the next to leading order term in the spin wave. So actually, we did two things. So in this ordered phases, actually they are non-collinear phase. So you have cubic corrections in the spin wave theory. So you can just do a mean field decoupling of this cubic term. When you do this, you actually end up with a Hamiltonian which is linear in the Holstein-Primakov bosons, and that suggests to you that your ground state is changing. So you have to renormalize your classical ground state because of these linear terms. And we also perform a spin wave theory in the polarized state. We come to the ordered state from the polarized state. In this case, because the state is collinear, actually we have to go to the fourth order term and just do the usual Hartree-Fock decoupling. And then what we look is the correction to the gap. So the point where the Magnon gap closes, the point where you have the transition to the ordered state. And then basically you just look how this guy changes. I mean, how this gap changes as we include this high order term. So that's essentially what you did. So on the ordered phase, what we did, we just calculate the renormalization of the classical angles. On the polarized phase, we just look how the gap change as we include these nonlinear corrections. So, and both of them we just treat at the mean field level. And what is interesting is that inside the ordered phase, so here it's clear the definition of the critical field is the point where the gap closes. Inside the ordered phase, we did the following. So we consider the critical field as defined by the point where the cosine of the renormalized angle, where you include the change, is equal to 1. So it's actually you spin points towards the angle. And that by expanding this quantity here, you can actually see the good quantity in this theory is not the critical field, but 1 over the critical field. So you really have an expression for 1 over the critical field in terms of the old field. So, and then you can calculate the 1 over S correction. So have those two. Principle, they are independent, similarly independent. But I mean, if we believe that this has to be a consistent theory, we expect them to agree. And that's precisely what happens. So this is, I'm plotting here C1, which is essentially the correction for the critical field. I gauge out the 1 over S. So this is in principle, if you want to a particular S, you just have to include it back. So this is just the coefficient of this expansion. So let's say we have a blue and black points. So the blue points, I come from consider the H3 correction coming from the, let's say, the ordered phase, and the black points, I come from the polarized phase. And you see they agree nicely, and they are always finite, except at the Kitaev points where you do have lots of fluctuation, then this is ill-defined, but far away from the Kitaev points here and here, you really see both definitions agree nicely. So it's all our interpretation, it's consistent. So what happens is that your critical field gets diminished. And we are also able to study the transition between the ordered phase, let's say the first order transitions. We did this, but just by comparing the renormalized energy. So we can also study the shift of the boundaries. I'll show this in a minute in our phase diagram. So now we can look to the magnetization curve before going to the phase diagram. It's really nice because you see, so this is like the Nel phase, this is zigzag phase, this is first spin. For a particular value of the interactions, this first spin 3/2, 1 and 1/2. So I'm decreasing the spin. And you can really see that the critical field is really reduced, and you can really see the magnetization is no longer saturated. So for this larger spin, you can even envisage some smooth interpolation between, let's say, the result in the polarized field, which I can carry out only at the classical critical field, and then you really see the diminution of the critical field, and then the theory becomes really well defined again. So the same happens for the zigzag phase, although here let's say the interpolation, it's not so obvious how to do it. So, and then as you decrease the spin, you see that you get a smaller and smaller critical field, but at least now the theory is consistent. What's hard to do, what we cannot do, is really to come up with a smooth curve that would require higher and higher order terms. But at least now we have a theory which is consistent in the sense that it diminishes the critical field, and the magnetization does not saturate as it should. So this is at least now we have a consistent theory. And then we can play around and draw the phase diagram for these few directions. First, I'll discuss the 0, 0, 1 direction. There are mainly three things which I'd like to call your attention to. First is that, so this weakly dotted line here, probably you can barely see, show the old boundaries, and you can really see the boundaries all pushing down, meaning that the critical field diminishes. All transitions here are second order, they're just pushed down. We have also first order phase transition between the order phase. This one I will not look into because here is the Kitaev point. In principle, have a spin liquid, so I won't discuss how this boundary changes, because this in principle is sort of ill-defined. But I can look how the boundary between the NL and the stripe phase change, and basically what happens, the NL phase is favored, so it kind of pushed the zigzag phase, so it increases. And also you can see that the close to the end of the zigzag point, I'll come back here, the correction to the field is actually negative, which means the critical field increases. So this is a kind of interesting result. So the zigzag phase actually, it's enhanced. So basically those are the main effects. This is for spin 2, 3/2. As you decrease your spin, for spin 1 and spin 1/2, you can really see that the effects become magnified, but they are all there. And I have kind of a really tiny yellow dots here, which I apologize for the size, which for the spin 1 is like for DMRG results. And you can really see that our spin wave results for the ordered phase, they kind of agree nicely DMRG. So when we increase these corrections, which I discussed, so your results become even quantitatively good as we compare, for instance, with DMRG, and also for spin 1/2, you can compare, for instance, to exact diagonalization. Mind you, I cannot discuss let's say the spin liquid, but the ordered phase, you see the frontiers, they are shifting the right direction. So these corrections, apparently this theory is not only internally consistent, but also produce quantitatively good results. For the 1-1-1 direction, situations is more involved because you now have more phases, but essentially you still have the same physics, that the NL phase is favored, the critical field is reduced, and the zigzag phase is enhanced. Okay, so that those are the main results. But now you also have some interesting things happening. So this green phase here is the vortex phase in the antiferromagnetic side. So as you diminish the spin, this actually goes away. So this is really suppressed by quantum fluctuations, which kind of nice result. And also you have this AF star phase here. The zigzag phase now wins over it. So it's strongly reduced in the presence of quantum fluctuations. So what's actually happening here is that all phases which have a smaller unit cell and which are present at the H=0 field, when you include these quantum fluctuations in a consistent fashion, they also start to increase a larger and larger portion in the phase diagram. So which is nice, but also which can be boring, because you'd like to observe some new phase. So it appears that it is unlikely to observe some interesting phase. The only phase which seems to survive, which is more robust, is the vortex phase. However, it's really strong close to the Kitaev point, so maybe it won't be there. So, but then we cannot answer this question at our level of theory. But anyway, so, and also I point out here, those are for the expert, those are just the climb points. That's essentially where this phase is fun out. Okay, so this is just for the experts. But anyway, so we are able to construct the phase diagram and more or less show. And again, we have a really nice agreement with the numerical results, exact results inside the ordered phase, showing this is a quantitatively accurate kind of approach. And just one last comment, which kind of more specific. This vortex phase, they are actually the angle. You have this pattern here, but it's not fixed on space. So in principle, you have a U1 degeneracy. So this is I'm showing this. The image is perpendicular to the field. And then in principle, although the relative angle between the spins is fixed, but you have a U1 degeneracy in the plane, and the overall angle is not fixed. So when you do order by disorder, you basically calculate the quantum correction to the ground state energy. Then you find 3 different minima, which correspond to patterns. For the vortex phase, basically what you have is the spins are parallel to the bonds of the honeycomb lattice, and for the AF vortex, the spins are perpendicular to the bonds. So that's what the order by disorder does to you. Okay, so this is fine. This was well known. But what's interesting, when you calculate this correction to the angles doing the cubic terms, when you calculate the corrections, your angle, your planar angle becomes undetermined again. So you do order by disorder in the first, and then you fix your classical angle. Then you correct your angles using the cubic term. Then you get your angle becomes undetermined again, and then you have to repeat the order by disorder. But now you have to go one order further. So you have to fix this angle order by order. So just it is interesting physics. Of course, each time you do this, the correction gets smaller and smaller. But it's interesting because, I mean, if you do order by disorder in a non-collinear phase, so if you correct the angle, then you have to fix it by going to one order higher in the energy. So you have to fix this order by order to do a consistent theory. This is just one curiosity for the experts, which comes out from our theory. So now I would like to, in the last 10 minutes or so, I'd like to discuss some recent work I've been doing in our group with Victor Meirelles. It's actually related to Kitaev material, but it's a different one. It's the hydrogen, lithium, iridium, oxygen 6. The thing about this material is that people have been trying to synthesize a iridate with hydrogen because of being lighter. So the expectation was you would get closer to the Kitaev limit, to the quantum spin liquid. So that's essentially the material I would like to discuss. So this was published in like 3 or 4 years ago. Basically, before that, you had some iridates. They were based on sodium and lithium, sodium iridate and lithium iridate. Both of them, they are Kitaev materials in the sense the Kitaev term is important, but they also have different terms, and the sodium orders on a zigzag fashion, and the lithium also orders, but the orders in a more complicated spiral phase. It's slightly more complicated, but at least for the sodium, we believe the Kitaev term is important, but it does order in the zigzag phase. But for this hydrogen lithium material, something interesting happens. So this is specific heat as a function of temperature. This is no field, and you actually see the specific heat over this Sommerfeld coefficient, like it's actually diverging as a power law. In this particular example, is like minus 0.5. It's diverging. You can calculate the susceptibility. Here is just a magnetization over field. It also diverges in a finite field, consistent to the same power law. And then when you apply a field, you suppress this power law. Okay, so it gets suppressed. And also, if you calculate the NMR relaxation rate 1 over T1, actually it's essentially it's almost flat. 1 over T1 times T is essentially almost flat. So all these points to a lots of low energy excitations in your system. So you have a pileup of low energy excitation. And then we'd like to discuss these results, assuming this material is described by the Kitaev Hamiltonian, but then we assume, well, of course, this cannot be the Kitaev spin liquid, because I mean, this in the Kitaev spin liquid, let's say the susceptibility would be constant, the specific heat would vanish linearly, and the NMR rate would be exponentially suppressed because of the Wison gap. But then we assume, okay, this cannot be the pure Kitaev model. So let's think about putting defects or disorder, but disorder in this part, I'll always refer to the usual disorder as defects, just to not confuse with the order by disorder and disorder in the sense of quantum spin liquid. So I'll just call these defects, which are inhomogeneous in your system. Okay, so that's how I would like to try to understand it. This is not our original idea. People did, there are some nice works. I'll refer to them. But before, let me just present to you the Hamiltonian I'm going to consider. So here I'll really use the Kitaev Hamiltonian written in terms of, let's say, the Majorana fermions. See, this C is here just the C0. So I have the Kitaev term. This kappa term here mimics an external magnetic field. So I show here there's actually a second neighbor hopping, but it is oriented hopping, so it's just like the Haldane model. So this is in principle that's where topology comes. And also I'll further perturb the model with a term which is K3 prime. This was proposed in this nice paper by the group of Christian Batista. So this term is nice because it preserves time reversal symmetry, and in principle in the spirit of effective field theories for the Kitaev model, which are first discussed in this paper. For instance, this is in principle this is a possible perturbation to your system. It's a third neighbor term, but the point here is just a perturbation which I can introduce, which preserves the solvability of the model. Okay, the model is still solvable, and then it preserves time reverse. I'll show why this is interesting in a second. So this is the kind of model which we are going to consider, just to make and if you ignore kappa and K3 prime, so you have what we call the Wison gap, which is the energy you have to pay to flip a spin. Whenever you flip a spin, you have to create a pair of vortex here, and then you have to pay this energy. This is the Wison gap, which people call. This is just the energy to create a flux, a pair of flux in your systems. So this here, there we have Monte Carlo results for the pure Kitaev model by the Tenazu, Udagawa, and Motomi's group. So in principle, the specific heat here have two peaks. One peak around, let's say, around K, which is kind of build up of short range correlation. The Majorana is starting to play, and the second peak here is just a crossover where you go into, let's say, the ground state of your system in the flux sector. So you go to the zero flux sector. So then this is just, you have this two peak structure. This is a log scale. And also they can calculate, for instance, the thermal conductivity, the Hall response, and they just increase kappa in this direction. And you see when you go below this temperature here, when you are in the ground state, you can really see your plateau developing here. So this in principle, you have the thermal response of your Kitaev model. So just to put things in a bit into perspective. And I point out, you see, there is no divergence in the specific heat. It's really well behaved. Principle goes to zero linearly. So that's what you expect in this model. So then what we did, we just perturbed this model, putting some bond disorder. So instead of just put disorder on the K on the Kitaev term, so instead of having K, I have K plus minus delta K. So this in principle is just binary disorder. So you could consider different disorders, just pick up binary, because from past experience, binary disorder generally tends to enhance the effects of disorder. And then since we are doing numerical simulation, small system size, this tends tends to get easier to analyze the results. And we are doing some simple calculation where we always assume a static flux configuration. So we have no flux dynamics. Okay, so in a sense, it's kind of variational, but I mean, we consider different flux configurations. But I mean, we assume a certain flux configuration, and then we diagonalize the Majorana problem. But I mean, there is no dynamics on the flux, and neither we consider the true, let's say, the true ground state. So I'll show. So here I just show the energy per site as a function of delta K, which is this disorder. And these I consider different flux. So let's say this black curve is zero flux, which is the ground state without disorder. And then the energy, and then in particular, this one flux here is the flux configuration where you have one flux per plaquette. So, which means you have one bond flipped per plaquette. So those are the two extremes. In between, you have what we call the random flux. So you have half of the hexagons have a flux, but in principle, these are random in space. So this is the green curve here. And you see, as increase the disorder, this kind of they mixed up. So for higher disorder, this was already pointed out in a nice work by the group of Matthias, and they realized they even point out that you must have a transition from the zero flux to the random flux. So in principle, you by playing around with the energy, you can more or less see that the flux sector kind of changed in the presence of disorder, even in this simple variational calculation. What's also interesting, you can calculate density of states of this density of state just for the matter or Majorana excitations. In a given flux configuration, I consider here two: random flux, which are full curves, zero flux, which are dashed curves, and different colors mean different values of disorder. So for no disorder, the zero flux goes to zero. It's just a linear distribution. If you have a zero, if you have random flux, it's slightly different, but it also goes to zero. It's not so clear to see. But then as you increase disorder, what happens especially for the random flux, you start to get some power law behavior in the density of states. So it's kind of divergent exponent alpha. So this is kind of similar to what's in experiments. So if you translate this to the specific heat, assuming that the flux are frozen, then you can translate this in the divergence of the specific heat. The same phenomenon also happens for the zero flux, but then the divergence is milder and you need a larger disorder to see it, but it's still there. So this is what we find. So this looks promising. And then we can play around and we can see that this power law, it actually depends on the parameters of your model. So that's why you play around with this K3 prime. For instance, you consider two values of K3 prime here for a certain value of disorder. The point is that if you change K3 prime, you change alpha. So remember, K3 prime is just a principle unallowed perturbation, which preserves time reversal. So, but the exponent alpha depends on it. So this kind of, it shows you the exponent depends on disorder and also K3 prime. So it's non-universal. And also, now it's interesting if you apply this kappa term, which would be an external field, and then things change dramatically, because for the random flux, you get a power law, it's suppressed, the alpha is diminished, but for the zero flux, you actually see let's say the topological gap emerging here. So actually you get the gap, which you get from the clean system. So disorder reduces it, but never closes it. So this is because this is a special kind, the bond is particle symmetric, so that's why it does not close the gap and neither creates states inside the gap. This change, for instance, if you consider vacancies. We can calculate the susceptibility, the static magnetic susceptibility, but for this model, slightly, you have to make some assumptions, because to calculate the spin excitations, as I explained, you have to flip a spin, then you have to create fluxes. So we use an adiabatic approximation, like people did in this paper. But it does not matter much. But I'm only telling you, you have to make at least a couple of assumptions when you calculate the spin excitation, just because you create fluxes. But if you work within this scenario, so for the zero flux, because you have this, basically in the zero flux, you have a Wison gap, which is different from the Majorana gap. This is just a gap to really create the excitations, to flip a bond. Below this, what happens is that your susceptibility saturates, as you expect for the clean model. Okay, so this is precisely what you expect. Disorder basically changes the value, but does not change qualitatively the behavior. But if you consider random flux background, it's nice. Then you really get power law, and it's the same power law you get from your density of states. What happens here is that for random flux, actually, this Wison gap is really too small, essentially zero. So basically, you never get to the below this, and then you get this nice power law, and it's the same exponent. So this kind of Griffiths-like scenario, for those who are familiar with these Griffith phases in disorder magnets. So it's kind of promising way of thinking about this. So that's how we are trying to understand this. And how can one generate power law distributions in this problem? So that's one natural question with your peers. So we did some simple exercise. What we did. So basically, we just diagonalize the Majorana problem for a finite system with just the Kitaev term, okay? And then, but you do this for open boundary condition. We use zigzag ends, okay? So just diagonalize your honeycomb lattice, free Majoranas, hopping, and it's really small systems and open boundary conditions. As one expect, the gap, you generate now at the Dirac points, you actually have a gap because the system is finite. and it decays exponentially with the system size. Okay, so just because you have now edge states, which are not topological, they see each other, you have a level crossing, and then this generates a gap. This generates a gap. As you increase the system size, the gap diminishes, and it does so exponentially in the system size L, where L is the size of a lattice. Remember, you're using periodic Pauli for this. Okay, so this is reasonable. People knew this. There's lots of works in graphene discussing this in really great detail. Okay, and then since we are talking about Griffith's phase, you can think about Griffith's like argument, but then you do that would be equivalent for those who are experts. So we're thinking about Griffith's phase inside an ordered phase. Okay, so how does that work? So imagine I have my system here. So this is blue, and this system had in all its ending. So you have a weak bond here coming out of my system. So this black region means we always have weak bonds. Here I can have stronger and weak bonds, but then what you have this, let's say, this island inside your system where you just have weak bonds at the boundary. Well, I mean, if we're talking about boundaries, then you can calculate the probability of finding such region, which is basically, I'm just put 1/2 because I'm using a bimodal distribution. This could be P, and it goes as the perimeter of this region. It goes with L. So you can write this as an exponential, right? So it's just an exponential rare region, but it scales with the linear system size. So so you have a gap with the case with the linear size. You have a rare region with exponential rare in the linear size. Well, if you play around, you can calculate your density of states or for excitations, you get a power law. Okay, and the exponential may be it can be negative. Just depends on how this actually depends on this. Let's say how you measure the probability and this coefficient of the exponential. In principle, it's possible, so you can at least generate a power law. So, but I have to tell you, this cannot be the ultimate fate of our system because it's really low temperatures. People figured out a long time ago, 20 years ago, not so long, that actually the density of states should have precisely this form. But what people also realize, it's really hard to see this numerically or because you really need to go to very, very, very low temperature and large system size. So probably this kind of power law is just a transient, but we hope this is relevant to the experiments, which means that's where actually the experiments occur. So, but I have to tell you that this is the correct response for this particular problem on bipartite lattice with bimodal with bond disorder. Okay, so which preserves particle symmetries. This is known, but on the other hand, people also know this is really hard to find. Okay, so that's one interesting thing. So we more or less understand how a power law can come about, even in this system, and it's also nice. It's kind of nice because it emerges naturally in this system. And also, just to finish up. So I'm sorry, I'm kind of talking too much. Just to finish, I would like to calculate, let's say, the topological properties of your system. So I'll calculate the topological number. So we use the so-called both index, which is more convenient when we are working real space. So we could use some real space implementation, the Chern number, but we decided to use the both index, which was, I believe, proposed in these two early papers by Hastings and Loring. And also, for instance, it's really convenient. People did this, for instance, in quasi-crystals, but it's a convenient way of calculate the topological number in real space. So here is the definition. Just have to calculate the projector. You have to calculate this matrix U and V, and then you get the both index. Okay, so find the definitions here. You can put this on a computer, and you can calculate the both index. Okay, so we can calculate this is the both index as a function of disorder for different values of K, which are the external field. And then if you consider a zero flux background, you see you always have a really nice, well-defined chiral edge state. So basically, because as I show here, because of the density of states always have this Majorana gap, so the topological gap is preserved even in the presence of disorder, and the both index. And of course, because this is topological, I can vary the K3 prime. It does not change. It should not, because topological does not depend on the details. But on the other hand, if you go to the random flux, Well, the but index is no longer quantized, and also it depends on the details. So it depends on disorder, it depends on K3 prime. So it tells you it's not topological. So what does that mean? So it means on the one hand, the random flux is more favors this power law behavior, which we discussed. So it's enhanced there. And also, it shows that you probably lose your topology there. So because you go to the random flux, you lose your topology. So this is more or less the scenario you have. And you can see this also. You can kind of look to this Cairo-Majorana Edmonds more or less directly. If you look to the, let's say, to the level spacing of your problem, this was original proposal by Prodan, Hughes, and Benevig. So this is what that would be the equivalent to look to the edge mode in K-space in a translation invariant system. When you put open boundary conditions, then you can see the edge mode. But since here we have a disordered problem, we can look this in an alternative fashion. So just look to the level spacing using the definition of level spacing by Uganese and Hughes. And there is which was, let's say, put on a firmer ground in this nice PRL here. And then, we can look here, does not matter much. There are several details, but the important point which I'd like to stress is the following. So this R here, it has two well-defined values. For the problem, we have what's called the Gaussian unitary ensemble. So that's the value which you expect, close to 0.6. And this is the value which you expect if your system were like, would have a Poisson-like distribution, which correspond to localized state, and that would correspond to extended states. Okay, and then you see if you have zero flux, as soon as you are out of the gap, you go to this unitary ensemble, which means you have an extended state. Well, at least suggests you have an extended state close to as soon as you leave the gap or inside the gap. So that we interpret this would be your Carol mode, okay, which gives you the both index. So then you have it. So it's consistent in the discussion. On the other hand, if you go to the random flux where you do not have a quantized system, a quantized topological index, you see, okay, it more or less it's close to the Gaussian unitary ensemble, but this probably is just a finite size effect, because when you increase the disorder, see, it goes down and tends to go to the Poisson limit. Just probably it's telling you really do not have a protected edge state in your system anymore. So now I come to my conclusions. So I just present you some try to convince you the Kitaev model is relevant to 4D5 and 5D5 materials. When you talk about materials, you have to consider extra terms, which they may affect non-topological properties, and then it's important to try to understand, to connect experiments to theory. We show a consistent one over S expansion, which is useful not only for the Kitaev model, but for any model which breaks time reverse, which breaks spin invariance. So this in principle is nice, so it's useful and could be applied to different frustrated magnets. There are proposals of Kitaev materials with larger spins, so the antimonades and the van der Waals magnets. I won't go into the details here whether this is relevant or not, but it's nice because so you can vary the spin. So if you apply the spin wave like theory, so in principle you can manage to vary the spin in a more or less easy fashion. And then I moved to a different iridate. So I asked if this order is relevant to it. And I showed that at least this power law behavior, which is seen in experiment, you can have this if you just consider the Kitaev model with a particular bond disorder. It's also true if you put vacancies. People did this, we also did this. So in principle, if you put disorder, you can generate this. And I showed this generates a non-trivial thermodynamics, not on specific heat, but also in the susceptibility. And also I didn't discuss much, but you can think about also the NMR. It's subtle, but it can be done. But what we learned is the following, that probably if you have a power law, it's likely, if this scenario is correct, that you do not have chiral edge mode. So you lose your topology because disorder essentially weakens the Wison gap. So you lose. So, but that would be interesting in experiments if you could measure it, because I mean, and also if you could somehow find different materials and change the power law, because I mean, in this scenario, the power law is no universal. If you come out with a universal power law, then you would have to change. That would be perhaps more interesting, but anyway, so we propose a no universal power law, which is not trivial, nice, but also would probably mean you lose your topology. Okay, with that, I finish, and I thank you all for your attention, and I apologize for going over 1 hour. Thank you so much.
Thank you very much, Eric. Now we have time for questions. Anyone have a question? Anyone has a question? Well, if not, we are a little bit over time. So thank you very much, Eric, again. You have a question?
I'm sorry. Yeah, I want to ask a question, but I didn't unmute. So I'm sorry about that.
Oh, sorry. No, feel free. Feel free.
So thank you for very nice talk, Eric. And I want to ask a few questions, if I may. So you talk about several broken symmetry states, like stripe states and stuff.
Yes.
Which are presumably for a given value of the tuning parameter, the lowest free energy states. But are there also, in classical systems with frustration, there are also sometimes metastable states which are not necessarily periodic, like self-generated velocity states, which are now known to exist in many models. So is there, has this been explored in this Kitaev type of situation?
Yes, thanks Vlad for the question. Yes, we actually do find some incommensurate states, or at least states with really large unit cells. We didn't consider this here to do the spin wave, but yes, so here I'm sure there is some region here when we actually have states which we're able to identify it has like a twin sites unit cell, or it may even be incommensurate. So in principle, yes, we can find these. So in principle, they could be here. But at least for these parameters we consider in this mod, it occupies a really tiny portion of the phase diagram, and most likely does not survive quantum fluctuation. But in principle, yes, it does appear here. Yes.
I understand, but I actually have in mind something different, that, if you are inside the one phase, like the stripe phase, there can be a minimum of the free energy, which is very far from your state. You're not saying that this should be the thermodynamically stable state, such a random state. These are almost never stable states, but they're metastable states, and they can be locally stable and very different than the uniform states. So to find them, you have to search for them. You cannot just look at the stability of the other phases, right? So has anyone thought of that?
I do not. I'm not aware, Vlad. I understand what you're asking. Thanks. I'm not aware. I'm not aware of this incommensurate phase inside this stripe as well. No, I didn't see discussed, but that may be my fault.
I see. Well, no, I mean, I know that we have done some related work over the years, and when I talk to many people who did spin ICs and stuff like this in fields, they find various phases, periodic phases. They look for the ground state. There are these metastable states, and for some reason, very few people in this kind of community have looked into this. But experimentally, this may be relevant, and entropically for everything. All right, never mind. The other question is, the 1/s expansion. There are other ways to do basically spin waves theory with the nonlinear spin waves theory. Like there are various, like Schwinger boson, various large N-tier versions that Sajda and others have explored. So have people actually tried different types of large N theories on the same models, to explore how these spin waves can, the nonlinear effects related to spin waves. So do you know of other theories?
Yeah, thanks, Vlad. That's a good question. So for the Kitaev model, I'm not aware. I know people have tried to do kind of Schwinger bosons, but not in this level of details we did, just because in principle, yes, it's true. One limitation our theory has is that we can only describe like ordered phase. So if you go like Schwinger bosons, for instance, then you could also describe the spin liquid phase. That would be nice. But no, people didn't do this as far as I know. So at least not consistently as we did. So just because it's kind of, as soon as you lose SU2 symmetry, it becomes slightly more complicated on a technical level. But no, people didn't do so. But that's why I emphasize we always look to the ordered phase and start this description. But the main technical complications that the Kitaev term, and then you really have to consider the in principle anisotropy. That the problem becomes harder. People have tried to do some Schwinger bosons, which in principle is nice because you could access the spin liquid, although the description would be not satisfactory because it's not bosonic. But no, Vlad, nothing so consistent, and the reason I believe is just because you choose broke.
Yes, I see. Well, I don't know. Maybe someone else has some other questions for some.
Thanks a lot.
Thanks a lot. I learned a lot. This was a very nice talk. Thank you.
Thank you.
Any other question? Last call.
Yeah, I see some questions in the chat, Chris.
Really?
In the YouTube chat. So.
Oh yeah, let me take a look at it.
I have it open here just in case I was following my connection.
Oh yeah, Pedro has a question. Can you also calculate the CT ratio in the disordered Kitaev model and check if you find a response that is qualitatively similar to that of the Nature paper in the H3 lithium, the second, I don't remember the.
Yeah, thanks, Pedro.
Compound.
Yeah, that's a really nice question. So in principle, yes, we can. Well, now it becomes trickier because we are really talking about low energy states here. So, but if you assume let's say your visors are frozen, okay, so there is no dynamics in your gauge field, then it's really the specific heat. This specific heat should directly follows the density of state. So in principle, yes, it should be similar to the Nature paper. So you can put parameters and you see it goes like that, and then you find the power law for lower energy. So true. So that's in principle possible. You can see more or less here it goes like that and then goes up. Those are probably clear. So in principle, the short answer is yes. We didn't do this just because then it becomes complicated as you go to larger temperatures. Then you have dynamics also in your visors that they are thermally excited. So the comparison is only meaningful at low temperatures, and then there it translates one-to-one. So in principle, you should get the same power law, and you should get that crossing point. So in principle, yes, it works. I cannot say it's just a very meaningful exercise just because you have so many. Principle had all the parameters, and as I discussed to you, this in principle is non-universal. So if you change like disorder or K3 prime, so you can change the exponent. So in this sense, what I'm trying to say is, yes, you expect to see a power law, but this is non-universal. So you can try to fit, but I'm not sure how meaningful that would be inside this scenario. So I'll need more information, like I need more quantities to compare to, because in principle, I need to fix like K3 prime or kappa, and in principle, can have a J as well. So it's kind of, I would say, slightly you pose problem, although it can be done. So I do not know, I'm trying to be very careful here, just because it's no universal. I do not know if it's satisfactory to you.
Another question that we have is Mal from Alwyn. Why the red dots drop beyond 12 T?
Okay, I believe this is the experiments, I think. So this. Yeah. Yes, this is just because when you go to the be above 12 Tesla, you get out of the topological phase. So basically you have three phases here. So that would be, let's say, the zigzag phase. Then you go into the topological phase. And then as you increase the field further, you go into the, let's say, the trivial phase, the paramagnetic phase. So you have a small window where you can find this topological phase. So that's where you have your plateau, which is kind of shown here. Above this, it drops. So and of course, this drop depends. You can see here, depends actually on the field directions. For this field direction, it drops. For this one, it does not drop. But that only means you are moving away from your topological region. You are entering the trivial or polarized state. So that's the reason. Or at least that's the interpretation.
Thank you, Eric. Well, we don't see any more questions on the YouTube and here, so I would like to thank you very much for starting your series again in this fall. For us, it's springtime. It's good. Thank you very much and hope to see you all next week. Next week, we have Alberto Nochera.
Thank you so much, Chrissy. Thank you all for attending this talk. Bye-bye.